Hi, this is going to be rather a long video. So consider the curve y is equal to ln of x squared over x. We're going to determine whether the curve cuts the x and y axis, find the first derivative and the second derivative, find the exact coordinates of any stationary points and determine the nature of such points, and find the exact coordinates of any inflection points, hence sketch the curve, state the domain and range, and we're going to investigate the concavity of the curve. Okay, at the end we'll have some GeoGebra app, and the link to that will be put in the notes of this video. So for the x-axis, y is equal to 0. That implies that ln of x squared is equal to 0 because x here, the denominator, cannot be equal to 0. And therefore, if we use log to the base a of b is equal to c, so write ln, so it's log to the base e of x squared is equal to 0, we know that that implies that a to the c is equal to b, and therefore the base here is e, so that will mean e to the 0 is equal to x squared. Now e to the 0 is 1, so we've got x squared is equal to 1, and therefore x will be equal to plus or minus 1. So therefore the curve will cross the x-axis at minus 1, 0 and 1, 0. So the y-axis, we've got x is equal to 0. So for y is equal to ln of x squared over x, we've already said that x cannot be equal to 0 because you can't divide by 0. The function, therefore, does not cross the y-axis, and the y is undefined when x is equal to 0, which means that the y-axis is called a vertical asymptote. B, if we use the quotient rule, because here we have a quotient u over v, and d dx of u over v is v du by dx minus u dv by dx divided by v squared. This is something that you really should learn and should just be able to roll it off your head. So dy by dx is going to be equal to v, which is x, times the derivative of ln of x squared. So that is 2x over x, using the rule for differentiating logs. Okay, and then we're going to have minus u, which is minus ln of x squared, times the derivative of x, which is 1, all over x squared, because v is x. Right, a bit of cancelling. That x squared will cancel with those two x's, so we're going to have with 2 ln of x squared over x squared. The second derivative, type u over v again, so we've got x squared times the derivative of 2 minus ln of x squared. The derivative of 2 is nothing, and therefore we've got minus 2x over x, minus u, which is 2 minus ln of x squared, times the derivative of v, which is 2x, all over v squared, so it's x squared squared. So a bit of cancelling. That x squared will cancel with that, and then there's a common factor of a 2x and a 2x here, so we'll take that out. We'll be left with a minus 1 there, minus 2, minus times the minus gives me a plus ln of x squared. That 2x has been taken out, over x to the 4th. So writing that out again. The x to the 4th would become x to the cube with that x, and we'll be left with 2 ln of x squared minus 3 from here. Right, for maximum minimum points or stationary points, okay, we will put the first derivative equal to 0. So that means that 2 minus ln of x squared over x squared is equal to 0. Now, the x squared can't be equal to 0, so we'll just check this bit here. So we've got 2 minus ln of x squared is equal to 0, which gives ln of x squared is equal to 2. Losing log to the base a of b is equal to c gives b is equal to a to the c. We're going to get ln x squared minus e to the x. It's going to give x to the minus e, or x to the e. So using the second derivative, be careful here also, if you take the 2 down in front, you'll miss one of the solutions if you're not careful. using the second derivative where x is equal to minus e. So using this, we just need to check the sign. So 2 times ln of minus e squared minus 3 over e to the cubed. So this, if you square that minus sign, it becomes positive. Therefore, you're just going to get 2 times 2 minus 3 over minus e to cubed. This becomes 2. If you take that 2 down to the front, then that will become ln of e. Or if you square it and then take the 2 down, it becomes 2 minus 3. So here on the top, we're going to have 2 over e to the 3. In fact, we're going to have a minus and divided by a minus. That's why it becomes out to be positive. So if that is positive in the second derivative test, that means the point is a minimum point. Just have to be careful if the second derivative comes out to be equal to 0. And then when x is equal to e, we're going to get the second derivative is 2 times ln of e squared minus 3 over e cubed, which give me, again, 2 times 2 minus 3 over e cubed, the same idea as before. This bit here will come out to be negative, so it will be minus 2 over e cubed. Now that means that this is a maximum point, because this is negative. Therefore, e is a maximum point. Right, when x is equal to minus e, then the y-coordinate will be ln of minus e squared over minus e. So square that, you're just going to get minus 2 over e. The minus sign comes from here. This will be positive. And similarly, when x is equal to e, y will be equal to e of x squared over e. This time this will be positive, it will be 2 over e. So the minimum point at minus e over minus 2 over e, and the maximum point at e 2 over e. For points of inflection, we need to check that the second derivative, where the second derivative is equal to 0. So this can't be equal to 0, that can't be equal to 0, so the only bit we need to check is this bit here. So ln of x squared minus 3 is equal to 0. That gives that ln of x squared is equal to 3. Again, using log to the base a of b is equal to c. B is equal to a to the c. We'll give that b, which is x squared, is equal e cubed. And to find x, we need to take the square root. And again, we're going to get a positive and a negative answer. So be careful, if you take that 2 down in front, you might miss one of the points of inflection. We should just check then that there's been a change of sign in the second derivative at that between those points. So when x is minus e to 3 over 2, when x is less than that, then the second derivative is negative. You can check this with a calculator by putting it into the second derivative. And when it's greater than, then the second derivative is 0. There's a change of sign. Therefore, x is minus 3 over 2 is a point of inflection. And similarly, when x is e to the plus e 3 over 2, same idea. When it's less than, you get this is less than 0. When it is greater than, you'll get that this is second derivative is greater than. A change of sign in the second derivative, and therefore it is a point of inflection. Find the y-coordinate. So when e is equal to minus e to the 3 over 2, you're going to have y is equal to ln of minus 3 over 2 squared. So the minus sign will become positive when you square it, and the 2's will disappear. So we're going to get minus 3 over e to the minus e to the 3 over 2. The minus sign comes from here. And when e is 3 to the 3 over 2, you're going to get that y is ln of 3 over 2 squared over e to the 3 over 2. And again, this will be positive, this will be positive, so you're just going to get 3 over e to the 3 over 2. So e minus e to the 3 over 2 and e cubed to the 3 e to the 3 over 2 are both points of inflection, non-stationary points of inflection. Okay, now to the sketch. Okay, so I did this GeoGebra app for that. So here we got this GeoGebra app. So here if we click on this, we can see that's the first derivative. So you can see that here you get a stationary point because the derivative is equal to 0. And here we seem to be missing one of the points here, but here it's equal to 0. I seem to have lost the point there, but never mind. Okay, and then when we do the second derivative, we get this point here, you get this point here, and this point here. We get what's known as a change of concavity. Now, why does that happen? Well, if we click to see the tangent, and we scroll the tangent along, here we can see the tangent is above the curve. Okay, at the particular point here, it crosses from one side to the other, and then it goes underneath the curve. And then it goes back on top of the curve again, still on top, still on top, still on top, and then at this particular point it will cross from one side to the other, and then you can see that it's underneath the curve. And that tells us about the concavity, and we can get that from looking at the second derivative. So here the second derivative is less than 0, concave downwards. At the point it will be 0. Here we get concave upwards, and here we get concave downwards. And here we get concave upwards, so we can see those points. So this GeoGebra app, I'll put in the notes of the video. I'll try and work out why it seemed to have lost a point there. There should be a point there. Okay, so the sketch is that. Okay, that's a sketch of it. So you would have to mark on the points where it crosses the axis. A minimum point over here. It just needs to be in right proportion. And then to work out, there's a point inflection here. And here, and here, you know, this is concave downwards, this is concave upwards. Now, the domain is every value of x is set 0. And the range is every value of y, again, except 0. Concave downwards is here and here. So it's x is less than minus 3 over 2 and x is greater than 3 over 2. And concave upwards is x being between minus 3 over 2 and 0, but not equal to these values, and between 0 and 3 over 2. Okay, quite a long video. So this has been a video to show you how to sketch a log graph. I hope you've understood, and I thank you very much for watching. The GeoGebra app will be in the notes of the video.